by 2 such that A transpose is identity, okay, and determinant of A is positive 1. I'm giving you this problem and asking you to prove that SO2 is a manifold, okay? A problem. Prove that SO2 is a manifold. Okay, let's take any element, any point. Here A is a 2 by 2 matrix, A1, A2, A3, A4, right? So I have 4 coordinates or 4 degrees of freedom, but they are subject to some constraints here. Let's talk about this equation. Here is A, here is A transpose, here is the identity, okay? And let's get equations out of that. So we have A1 squared plus A2 squared is unity. We have A1, A3 plus A2, A4 is 0. And we have A2 squared plus A4 squared is unity. The determinant being plus 1 gives you just a side condition. It's not an independent condition. If you just look at the equations, you can realize it, but we'll not discuss it here. The determinant is A1, A4 minus A2, A3. This has to be positive 1, not negative 1. So I have 4 free parameters subject to 3 green constraints. So how many degrees of freedom overall do we have? So if this is a space and I want to know its dimension, meaning how many degrees of freedom I have to move in that space. Well, it's 4 coordinates subject to 3 equations that have to be satisfied. So it's only 1, right? It's like here in the plane, we have everything characterized by x and y, but we have a condition, x squared plus y squared is 1. So 2 free parameters subject to 1 constraint gives you 1 degree free. So this is one-dimensional manifold. SO2 is one-dimensional manifold. Let's see how to prove that it's a manifold.
So would that 1 degree of freedom be like theta?
Exactly. We're going to show that now in a minute. So, I have 3 equations. Well, what about projecting on A1? So let's have U1 is, so I have A1, A2, A3, A4. It's like 4 numbers, but I'm going to projecting on 1, because at the end of the day, we said that it's 1 degree of freedom, right? So I'm going to project on 1 and try to get the rest of the 3. So U1 is, you're going to take A1 and then you'll try to construct the A1, A2, A3, A4 out of just A1 only, right? Well, A1 is A1. What about A2? I'll get A2 from here, right? Which is square root 1 minus A1 squared. And it's positive or negative. So you have to specify now which neighborhood you're talking about. So I'll take that, well, it's every A1, A2, A3, A4, but A2, I'll take the positive and then I'll do something later, the negative and so on, so like we did with the circle, okay? Yes, Mikhail?
You say that we have 1 degree of freedom because we only have 3 equations.
Yes.
What about the right equation?
It's not an extra equation, it's one piece.
So it's just a combination.
Yes. So, what's your phi 1? Phi 1 will take A1, A2, A3, A4. We decided that I'm going to project on the A1, so this is very easy. What about phi 1 inverse? It takes A1 and should give you 4 numbers, right? Okay? Please bear with me here for a minute. What's this guy?
A1.
A1, that's fine. What's this guy?
1 minus
This should be A2, and from these equations, it's completely characterized from A1 as 1 minus A1 squared, correct? And this you need to solve. Now, these 2 equations together, you will have 2 solutions. one that gives you this collection as positive 1, and one that gives you this collection as negative 1. Obviously, we're talking the positive 1, 1, and the positive 1 solution is A3 is negative, and A4 is A1. Okay? If you solve them together, I will just save some time. So here is the thing. Okay? So phi 1 inverse takes just a single element and give you the whole matrix, right? What's the whole matrix? Give you this guy here, this guy there, this guy here, this guy there, right? Anything so far? Any questions so far, please? Any question? Yeah, so very good. We proved, we got the first neighborhood and the first map. You go and do the rest of the things. Probably it will need 4 maps like here, at least. And then we're done. It's a manifold, really, and one-dimensional manifold. Just want you to notice something here. If I call the A1 as a cosine theta, what would be this guy? Sine, right? And this negative sine. And this cosine. It's our lovely block, cosine, sine, negative sine, cosine. It's rotation matrix at the end of the day. It's SO2. Just 2 dimensions. Okay? Okay, so what's the take-home message from here? Well, a manifold can be a very abstract object. And we know the very precise definition that at every point, locally around the point, I have to relate it to a flat space where everything is nice. Okay? We spent much time with the first word, manifold. We're going to go to the second word now. It's really a language. It's really a language that we learn. Hopefully, when we speak this language, we'll get some benefit at the end. Einstein did. Get the best benefit ever. Okay, the second word, it's not as hard actually. A curve. This is the second one, curve. Let's define it. So a curve, gamma on M. Curve in M. So this is M. And we have a curve. This is actually a very intuitive definition. We have a curve that passes through a point. So mathematics in general actually has nothing to do with differential geometry. A curve is a map actually. Gamma from any interval, say from 0 to t, any interval on the real line, okay, to your M. That's it. So we have a real line, just one dimension, has nothing to do with the manifold. The manifold can be any dimension, but this is just one real value. It's like time actually. Think of it as time. It takes time and gives you this guy. So here is the real line, maybe time, and this is the gamma that takes, as the time evolves here, the gamma gives you a point evolving there. Okay. Example, please. This is straightforward. Maybe here's a sphere. Here's an example for gamma on S2 on the sphere. Gamma of t is t. It's 3 points on the sphere, three coordinates. T over 2, and maybe square root 1 minus 5t squared over 4. So actually, gamma of 0 is this point P, the North Pole. Gamma of 0 is 0, 0, 1. the curve. As time evolves, as time is a real number, right? As time evolves on the real number, if this is x here, well, and this is y, this guy does the following. This is your gamma, okay? It's a curve on the sphere, curve on the manifold. Very intuitive thing. Just we're doing it very formally. It's a map from real line, time, to your manifold. Interesting thing is that when it comes to abstract objects like this, it's a curve that passes through matrices, right? It's every point is a matrix. Actually, this is not that fancy. It's simply your R of t, right? I'm giving you the rotation matrix as a function of time, and each time I have a matrix. We call this a curve in the spatial orthogonal matrices. That's fine, right? It's a curve passing through these matrices. You have any question about the definition of a curve? Any question? It's not that a problem actually, or not that, it's not weird, it's not, it's okay I think. Here is the thing that may be new. The third word, tangent space. This is a little bit weird, no, not weird actually, it's just a little bit new. Tangent space. And we're actually defining the tangent space of M at P. We're defining it at points and giving it the name TPM. We really stress the point T. We're defining it at a point. And this has the very intuitive definition, which is if you have a surface in Rn, this is really the tangent. So at this point, here is the tangent. At that point, here is the tangent plane. That point, here is the tangent plane. Is the tangent plane. Okay? This is the tangent space at a point. At a point. So you can see that this plane is different from that plane, is different from that plane. So the tangent space really depends on the point. So yeah, I can easily visualize the tangent space of my manifold if my manifold is a surface. Is the tangent plane to that surface, right? What about if your manifold is a space of orthogonal matrices? It's a very abstract object like this. What is the tangent space? So we need to make this definition very formal, okay? That is not only applicable to surfaces in Rn, but also to other objects, as long as they are manifolds. They abide by your definitions of a manifold. Okay, so what is the tangent space, tangent plane at this matrix? Well, this is very hard to visualize, right? So we need to have a mathematical definition. Actually, the mathematical definition is also intuitive. What's that? Since you can define a curve on a manifold, I can define a curve on any manifold, or even here, I can define a curve, right? Well, it will be, the tangent space will be the space of all velocities of curves passing through P. So at this point, just bear with me here for a minute. At this point, I have a curve passing through the point. We'll get the velocity at this point, please. This is one vector in the space. I have another curve that's passing through this point. Here it is. Well, I need the velocity at this point particularly. This is another vector in that space, and so on and so forth. So the space composed of all these velocity vectors give you the tangent plane formally. Here and there, because here still I have gamma of t, so I can differentiate it to get the velocity gamma dot and evaluate at the point, right? R dot at the point. And see all these velocity vectors, my space is composed of these vectors. So the tangent space is not composed of points, it's composed of vectors, and this is very important. The tangent space is a vector space, meaning a vector space you can add things together. So in the tangent space, I can add vectors together and multiply by constants. I can add things together.
Is the tangent space flat?
Yeah, it's a flat space. It's a vector space. So you can add things together, yes. It's not completely Euclidean in the sense that so far we didn't say anything about measuring distance or angle between vectors, but I can add vectors. They are velocity vectors and I can add velocity vectors. This is all what we know.
Is the tangent space also Rn?
No, this what I'm saying is that it's less, a little bit less quality than Rn. In Rn, this is an important thing, I guess. In Rn, I can do all the following. And we're going to talk about this in detail later, but here is just a glimpse. I can add points, P1 plus P2, or V1 plus V2, vectors or points, right? This characteristic only, plus scalar multiplication, if you can multiply by scalar, 3, 4, this characteristic only, we call it a vector space, okay? But I can do more in Rn. I can measure distance. This is called vector space. This is called, as you can see, metric space, right? Not only distances. I can also do dot product or get angle between vectors, angles. Okay? This is what we called, this is metric, this is inner product space. I can do inner product, dot product. So if you have this, actually, we will show later, if you can't do the angles, then of course you can do the distance, and of course you can add. But if you can have this only, it's not necessary that you can have distance and so on. So Euclidean space you can do all. I always relate these to, countries and say, okay, you have countries that are very civilized. You go the distances between points that they are known, and the angles they are known. And if you go to maybe a poorer country, well, things are, it's not just measured by angles, maybe only distances and so on. So there is actually space here that you can do nothing. This is what we call topological space. Okay. At any rate, don't take for granted that we can do all the mathematical operations that we learn on any space. They are only on Euclidean space. This is the best space ever.